We are Group 16, and our final year project is titled Decoding Brain Connectivity in ASD, a deep learning and clustering approach using EEG. I'm Dvisha Shah, and this work was done under the guidance of Dr. Kriti Srivastav, along with my teammates Meeram Ranka and Soumya Dadich. Advances in technology have opened up new possibilities for understanding the complexities of the human brain and addressing critical challenges in healthcare. Our focus is on developing an EEG based computational model for detecting neurodisorders, with a particular emphasis on autism spectrum disorder or ASD. Neurodisorders are a growing concern globally, and their impact on individuals is profound. Our focus is on ASD as it is a condition that affects how people communicate, interact socially, and behave. Early detection is critical for timely intervention and personalized care. Diagnosing ASD can be challenging because it's typically based on subjective behavioral assessments. We aim to change that by introducing a more objective, data driven approach using EEG signals. Gap analysis. While there is existing research on EEG based ASD detection, it often suffers from key limitations. Data pre-processing steps vary widely, leading to bias and poor model convergence. Many models either oversimplify the problem with binary classification or lack interpretability. Crucially, most ignore severity classification, which is vital for personalized care. Our work addresses these gaps through deep learning and clustering. Problem definition and objectives. Despite the advancements in understanding ASD, current diagnostic tools have several limitations. Diagnosis often rely on subjective behavioral assessments, leading to inconsistencies. There is no standardized method to measure the severity of ASD, which is crucial for personalized treatment plans. Existing tools fail to utilize EEG effectively for both detection and severity classification. So, the objectives of this project is first, to use EEG to analyze brain activity patterns, including ERP signals. Second, to build an ASD detection model, which is a deep learning model to detect the presence of ASD. Third, to extend the functionality of the model to categorize ASD into severity levels of mild or high based on EEG signal abnormalities.
Yeah, so diving into the dataset was particularly interesting. For our project, we used EEG dataset titled Early and Late Stage Processing Abnormalities. It includes EEG recordings of 34 children, with 15 diagnosed with ASD and 19 typically developing children. These recordings were captured during the visual stimulus experiments. So it was basically where children were shown images of objects like fruits and vegetables. The dataset comes in a brain vision format, which provides raw EEG signals, event markers for stimulus onset, and metadata like sampling rate and electrode placements. The EEGs were recorded at a sampling rate of 500 Hz using a 64-channel system, based on the International 1020 system, giving us high resolution and spatial and temporal brain data. This dataset is rich in both raw signals and behavioral event context, making it ideal for machine learning based ASD analysis. Next slide, please. So our proposed system is divided into three main components: dataset description, pre-processing, and model building and implementation. I'll explain the pre-processing. So EEG data, as you all know, can be very noisy. Pre-processing is a critical step. We started with bandpass filtering between 0.5 and 50 Hz, which removes unwanted low-frequency drifts and high-frequency noise. Then, we used independent component analysis (ICA) to eliminate artifacts like muscle activity or power line noise interference. After that, we performed epoching, segmenting the EEG around stimulus events from 200 milliseconds before to 800 milliseconds after the visual cue. Next page, please.
The proposed design. Our proposed design is structured into two key stages, one for detecting ASD and the other for analyzing its severity. So on the ERP components that are central to our analysis, event-related potentials are specific brain responses that occur in the relation to stimuli and provide insights into cognitive processing. So we analyzed four major ERP components, which is P100, N100, P300, and N400. So as you all can see on the plot, the blue line represents the ERP waveform of a typically developing child, which clearly shows sharp peaks. In contrast, the red line shows ASD response, which is generally delayed across the four components. This visual difference reinforces how ERP features are critical indications in ASD detection. Now I will explain the stage 1 of our model, which is the ASD detection model. So in stage 1, the primary goal is to build a model that can distinguish children with ASD from typically developing. So here is how we create the input for our model. For each EEG recording, we divide the continuous signals into 1 second segments. Then for each segment, we calculate the functional connectivity using Pearson's correlation coefficient. So functional connectivity measures how different brain regions interact over time. Research shows that brain networks are altered during ASD. So overconnectivity or underconnectivity in a specific brain region can help us differentiate from ASD and TD. So high connectivity between regions may indicate strong neural communication. So we have used functional connectivity and converted it into a matrix using grayscaling so that it is an input for our ASD model. We have used the CNN LSTM model for detection of ASD. The CNN layers learn spatial features such as clusters or disconnections, and the output is passed to an LSTM network which captures these spatial features, how these features evolve over time. To prevent overfitting, we use dropout layers, and we have used an Adam optimizer with binary cross entropy. The final classification uses a fully connected layer and a sigmoid activation, which gives a probability score of ASD or TD. Our initial model had decent performance, but we optimized it further for better accuracy. These improvements led to a boost in classification accuracy from the earlier values and giving us a final accuracy score of 91%. We'll further see the performance analysis in the next slide. So the performance analysis states the model performance, which gives an accuracy of 91% and a precision of 87 and 96% respectively. So these metrics show a well-balanced model that is both sensitive and specific. We also analyzed an ROC curve, which yielded an AOC score of 0.98, which is close to perfect classification. This proves that the model can reliably differentiate between ASD and TD participants. Also validated our results statistically using hypothesis testing. Our null hypothesis stated that the model would fail to achieve an F1 score above 80%, and the alternate hypothesis stated that the model would succeed. So as we got an F1 score of 92% and 89% respectively, we confidently reject the null hypothesis and accept the alternate. The high AUC value further confirms the model's strength in detecting ASD using ERP and EEG features.
After detecting whether a subject has ASD or not in stage 1, we move to stage 2, which focuses on assessing the severity of ASD. Since ASD is a spectrum disorder, identifying its severity is crucial for early intervention and personalized therapy. Next page. This stage involves converting EEG data into functional connectivity matrices and then using unsupervised clustering to group ASD subjects based on severity patterns. Here's the pipeline for our severity detection model. First, the pre-processing of FC matrices to clean and normalize connectivity matrices derived from the EEG data. Then we perform feature selection and reduce dimensionality. Finally, the main stage is the group separation and clustering by applying unsupervised learning techniques such as k-means and hierarchical clustering. Next page, please. So we transformed our EEG signals into FC matrices and plotted our clusters using a TSNE visualization. As you can see that there are two clusters formed. First, the blue cluster is for ASD and the other cluster is for the TD individuals. We evaluated a clustering model using a silhouette score, which measures how similar an object is to its own cluster. Our model achieved a silhouette score of 0.67, which is well above the threshold of 0.5, indicating good clustering performance. As you can see from the diagram below, which shows clearly separated clusters. Next page, please. Next. To statistically validate our clustering results, we defined the following hypothesis. Null hypothesis suggests that functional connectivity features do not produce meaningful clustering results. That is, silhouette score will be less than 0.5. An alternate hypothesis suggests that they do, which means silhouette score of greater than 0.5. Since our silhouette score will be greater than 0.67, we reject the null hypothesis and accept the H1 hypothesis. Next page. In conclusion, we achieved a 91% accuracy in detecting ASD using EEG-based deep learning approach and introduced a novel clustering approach for ASD severity assessment. Our future work involves integrating EEG data with behavioral assessments, eye tracking, or fMRI to enhance classification reliability. We also envision adapting this system for diagnosing other neurodevelopmental disorders or offering personalized therapy recommendations based on severity levels. Thank you.